Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, it's a great pleasure to welcome you all to this, the third in our series of distinguished lectures. We had Leslie Lamport back in May, shortly after the award of he received his Turing Award, and we had Ara Darzi in November. Very different kind of talk. Today we have Tony, about whom more in a moment. And in May, we have Bernard Schilkopf coming, who just won the third Robin Milner Award, which, as you may know, is the top award for computer science in Europe. But now to Tony, who is the main subject of the day. You can see how long his CV is, and I can't possibly deliver all of this. I guess it may be well known that he began studying classics. I suppose at the time he couldn't have studied computer science if he'd wanted to, because it wasn't really there. Because he's done so much actually to construct the subject so that now that we can teach it. So he began, as I said, with classics, and he became an expert in Russian in the Navy. And his first job was with Elliot 803, perhaps, was it? 803, where he first worked on Algol, and his first academic job was at Queen's University Belfast, where he was a professor, eventually coming back to Oxford, and from where Microsoft poached him, although there's always a dispute about that, about whether Oxford says he retired, we say we poached him. But, anyway, we've enjoyed very much having him here for the last 15 years. He is so well known for many things that are household words in computer science, like quicksort, CSP, and many others, and has a great list of honours and awards. There's his knighthood. Perhaps the most rarefied one is the Kyoto Prize. I think that's rather rarer than the Turing Award. But at this point I'll stop, because there are still many more pages to go. And Tony, we're really looking forward to the lecture, so let's get on with that. Thanks very much.
Well, thank you very much for that kind introduction. And thank you for inviting me to deliver this lecture to a distinguished academic and industrial audience. Among you are many friends and colleagues working with me in Microsoft Research, as well as members of the Cambridge University Computing Laboratory, of which I am proud to be an honorary member. Others are industrial visitors from the flourishing computer and software industry, which in and around Cambridge. Welcome to you all. I have spent, as Andrew described, a bit less than half my extended working career employed in industry, and a bit more than a half as a university professor. I therefore really relish this opportunity to talk to a mixed industrial and academic audience on a subject which has been dear to my heart throughout my varied career. I hope in my talk to interest my academic audience in the idea that the laws of programming are simple enough to be taught to computer science undergraduates, maybe in their introductory courses. And I hope to interest my industrial audience in the idea that the laws can be useful to software developers, particularly those designing, writing, or debugging concurrent programs. My original motivation for exploration of the laws of programming was scientific curiosity. Discovery of the laws of nature has been adopted as the primary goal of the natural sciences ever since they broke away from other branches of philosophy. The foundations of many well-established scientific disciplines is now codified in the form of elegant algebraic equations or inequalities, as illustrated by the examples on this slide. The laws of nature are all applied pervasively in engineering applications of those branches of science. They provide the scientific justification for the algorithms that are embedded in a modern engineering design automation system. Such a software system calculates the consequences of the laws when applied to particular designs, products, and services of current concern to the engineer who uses them. I suggest that the laws of programming provide a foundation for the science of computing in the same way as the laws of nature for other branches of science. And they are already providing software development engineers a range of algorithms for the integrated development environments like Visual Studio and Eclipse. I shall present a selection of simple laws from sources shown on this slide. These sources are familiar to many computer scientists, both of practical and a theoretical inclination, but I won't assume from my audience any familiarity with any of them. I will, of course, throughout the lecture be paying special attention to concurrency. So, my summary. I will have 5 headings. The first will tell you what are the laws of programming. The second one with concurrency. The third one will answer the question, what are they for? The next one, what's the point? And finally, consider an argument against. So what are they? The laws of programming are a collection of algebraic equations and inequalities that hold between computer programs, in the same way as the laws of arithmetic hold between numbers when they are when arithmetic is done on them. So, as my running example, I will choose the natural numbers, just the non-negative integers, which you are surely familiar with. And my aim is to show the broad overlap between the laws of arithmetic, which are taught to school children, and the laws of programming, which are not yet taught even to undergraduates. As an example, I will give the laws for natural numbers, and my arithmetic operators will be confined to just 2 of them, multiplication and addition, and my only relation between the numbers will be their numerical ordering in order of magnitude. When the same laws are applied to computer programs, the basic commands of the programming language will serve as constants of the algebra, the assignments, the inputs, the outputs, and the jumps, and so on. They obey many elegant algebraic laws, but I shall ignore them completely, except for 2 basic commands named as they were on the previous slide. So the 1 and the 0. The 1 stands for a very pervasive command in programming, which is do nothing, and 0 stands for a program which has no executions, maybe because the compiler has found a fault in them, say a type mismatch, which means that they are inhibited from reaching any execution. There are 3 basic operators that compose the basic command. The semicolon and the parallel signs specify complete execution of both their operands, either sequentially or concurrently. The union operator presents a choice between its operands. Now, the criterion for the choice is left entirely unspecified. It must be therefore regarded by the programmer as a completely non-deterministic choice made by the implementation perhaps at any time, for example at compile time or even at runtime. Now, the ordering relation states that everything that the left-hand side, P, can do can also be done by the right-hand side, Q. If Q is being used as a specification of the behavior of the desired program, then the ordering relation means that P satisfies its specification. If P is non-zero, another use for a law, an inequation, is that if P is non-zero, a compiler is permitted to, or indeed an instruction pipeline is permitted to replace Q, the more non-deterministic one, by the more deterministic P. The reason for doing this is, of course, usually in the hope that P will be the more efficient. Thus, the laws, the inequational laws, can be used as valid transformations, or indeed the equational laws, for optimizing programs. And every programmer who uses an optimizing compiler may hope that the compiler is performing valid optimizations according to the laws. So here are the laws for multiplication of natural numbers. I will claim that these, the three laws I'm sure you're familiar with, and I will claim that they also apply to the two forms of program composition, both parallel and the sequential, denoted by semicolon, when you substitute these two symbols for the multiplication symbol in each formula, which I think I will do now. On this slide, multiplication is substituted by sequential composition of programs, and the explanation of the laws is still quite intuitive. First, for the unit law, doing nothing, either before or after doing something, is the same as doing that same thing, P. For the associative law, I reason that doing three actions in sequence is the same as doing the first one first, followed by the other two sequentially. It is also the same as doing the last one last, preceded by the other two performed sequentially. Finally, if a program has no executions, then the same is true of any program which contains that as a subprogram. This is because each of my composition operators requires complete execution of both its operands. And if one operand has no executions, that can't be done. Now, a similar intuitive explanation justifies the laws for concurrency. The last law on this slide states that programs executed concurrently may be written in either order. Doing something at the same time as something else is the same thing as doing something else at the same time as something. And finally, the laws for addition, which will be similar to laws for the non-deterministic choice operator. The first three laws are remarkably similar to the ones we've already seen, except that zero is the unit of addition. The final two laws on this slide are familiar distributive laws. They say that if you are multiplying a sum, this is the same as taking the sum of the component-wise products. And in fact, what this reinforces, this is an instance of my statement that non-deterministic choice may be made at any time, either before or after doing the multiplication. The first two of these laws are obtained simply by are the associative and commutative laws for choice. Obviously, offering a choice between P and Q is the same as offering a choice between Q and P, and offering a choice between P and the choice between Q and R is the same as doing it the other way around. The third law says that if one of the alternatives has no executions, then the non-deterministic choice will always select the one that has an execution. It can't do anything else. This is something like Henry Ford's famous statement: you can have any color. You can have any color except. Sorry, I've just misplaced that quotation. Excuse me. As long as it's black, thank you. That may be a description of the next law as well. The final law is one that is not true of addition of numbers and really has quite impressive consequences. It's the statement that the choice between P and P is the same as P itself. It is no choice at all. Finally, we have the distribution laws, which can be written as saying that that either semicolon or concurrency distributes through choice. The choice can be made before embarking on the concurrent execution or during the concurrent execution as necessary. Now, the ordering relation can be defined in terms of choice, as shown on the first line of this slide. Using this definition, other familiar properties of the arithmetic ordering of numbers can be proved as theorems. The laws on the last line of this slide says that if you increase the determinacy of a component of a program composition, for example, by removing the alternative Q, that's on this, if you remove the alternative Q, you can only decrease the, you increase the determinacy of P union Q, decrease its non-determinacy. Now the final two laws, say that concurrency and sequential composition are covariant in the sense that if you increase the determinacy of one of the components, you can only increase the determinacy of the other component or leave it the same. This law is true for both sequential composition and concurrent composition, and indeed for multiplication if the or sign is replaced by the sum. The most important properties of ordering are described by proof rules, which can be proved in advance of using them from the laws of the previous slide. Each rule consists of one or more antecedents, which are written above the line, and one or more consequents, which are written below the line, above and below. Each rule says that the consequence written below the line can be proved simply by proving all the antecedents above the line. The advantage of a proof rule is that it suggests a tactic for the proof of the conclusion. For example, the first rule of transitivity, shown here, says that if you want to prove that P is below Q, so I've got P below, if you want to prove that P is below R, then it may help to find an intermediate formula Q, which is above P and below Q. And if you can do that, you already have made a proof that P is below R. Another advantage of the proof rule is that your proof can then make explicit reference to the rule, which can make the proof quite a bit shorter to the benefit of both man and machine. Now the covariance rule, this one, is a direct consequence of the covariance law. It states that if the determinacy of either of the operands of, say, Q of a composition is decreased, the determinacy of the result remains unchanged, or it decreases. This is the rule that justifies an engineer in replacing any component of a working system by a component that has tighter tolerances than it, thereby reducing its non-determinacy, making it more deterministic. The resulting system with the new component, let's come back. The resulting system with the new component is, what have we got here? The new component P is still more deterministic, has tighter tolerances than the original system with the component that has been replaced. And that's a fundamental belief of every engineer. If it turns out that replacing a component with one in which the supplier has promised that it has tighter tolerances, if that actually increases the non-determinicity of the whole system, then the claim that the tolerances were tighter has been refuted. You should return the component with a rude note. So now let's come to the fundamental law that governs concurrency in a programming. It's called the exchange axiom. I call it the exchange axiom. It's been discovered many times independently, and everybody gives it a different name, I'm afraid. I'm not particularly proud of my one. This is the axiom that justifies the interleaving of atomic actions as an implementation method for concurrency, as I will show. The exchange law, which I've written as an axiom here, says that the concurrent composition of two sequential compositions on the right-hand side, the concurrent can be made more deterministic. One of the ways of implementing it is to compose two concurrent compositions, where the first operand of the sequential composition contains everything that is done up to the semicolon by both the threads on the right-hand side, and similarly the concurrent composition after the semicolon are the two obtained from the sequential composition of the right-hand side. So the role of concurrent composition and sequential composition has been interchanged between the right-hand side and the left-hand side. That's why I call it the exchange law. The shape of this theorem is actually quite familiar to you, and indeed to all school children in Britain these days, because of the theorem that if you add two products, you get a number which is less than the result of summing them and then multiplying them together. So plays the role here of the concurrent composition. Here's the axiom again with another explanation. The left-hand side of the inequation here is an interleaving implementation of the more general concurrency on the right-hand side. And what has happened is that the implementation, the scheduler, which schedules these concurrent compositions has chosen these two semicolons as a sort of barrier which the two threads must pass simultaneously. On the left-hand side, this is stated that when that semicolon is reached, this single semicolon here stands for passing both of these semicolons on the right-hand side, so they can be merged into one, and before this semicolon there occur all the actions of the first components of the sequential compositions of each thread, and on the right-hand side we have the second components of each of the threads. The use of implication in this law rather than equality is essential because this also allows alternative implementations of the right-hand side, and it's non-deterministic which of the scheduling strategies will actually be adopted. In fact, the laws do not preclude true concurrency, which could occur if there is synchronized execution of events such as input and output between the operators in a communicating process framework. The exchange axiom has some simple and extremely useful consequences called frame laws. I've written the axiom again at the top of the slide. The frame laws are easily proved from the axiom using the fact that 1 is the unit of both sequential and concurrent composition. For example, if you replace the p dashed on both sides of this equation by 1, then the two ones cancel with concurrent or sequential composition, and the result is exactly what we have claimed to be the first of the frame theorems. This is an alternative with Q treated in the same way as P dashed was. And here we've done it twice to get the basic laws that sequential composition is more deterministic than concurrent execution, and similarly the other way around. Those are the two. If P and Q are basic commands, this is merely an interleaving law for the implementation of concurrent composition. Of course, it may happen that the sequential composition here has no executions at all. For example, if P is the destination of a jump, perhaps I'll just leave the example out and go on to the next slide. So I'll show you a more extended example of how the exchange law justifies the interleaving of its operands. So I'm going to consider two strings, ABCD, written in red, and XYZW, and I'll assume that these are atomic operations in the program. And these two programs are executed concurrently, and I will show you just one of the interleavings of actions which the exchange law permits. At the top, we've just written the concurrent composition of the two strings. In the second line, we choose the semicolons to indicate the point at which we're going to apply the exchange law. That's permitted because a sequential composition is associative, and we can put that semicolon anywhere. Here we apply the exchange law once. We take the first part of the second operand and run it concurrently with the first part of the first operand, and similarly on the right-hand side of the semicolon. And that is actually equal to, we make an arbitrary choice of splitting the xy in the middle and splitting the BCD as shown by this semicolon. Finally, not finally, an application of the exchange law now allows us to the frame law allows us to bring out the y to be done after the concurrent execution of the other two basic actions, and similarly on the right-hand side. And finally, applying the same frame law twice, we can get an example such as x, as shown here. Notice that the ordering of the individual threads has been preserved in the interleaving, as one of the necessary conditions of the correctness of interleaving. But these choices of where to put the semicolon and whether to commute the operands of parallel composition in one way or another, these are made during the proof, and different choices of commuting the concurrent or selecting the sequential compositions will give you eventually all the different interleavings that you can get from these two threads. Now this, the exchange law can be presented, instead of being an algebraic law, it can be presented as a proof rule, as shown on this slide. Like the rules for ordering, the modularity rule provides a strategy for structuring a proof of its consequence into smaller and simpler parts. Each of the two antecedents of the rule above the line is smaller than the consequent, because each of them contains only 3 operands instead of 6. And they're simpler because they involve sequential composition rather than concurrent. Now, it's surprisingly easy to derive the exchange law and the modularity rule from each other, as I will show on the next 2 slides. First, here is a proof of 1/2 of the equivalence. It starts with the modularity rule, which I've copied on the top of this slide. Since it is a general rule, we can replace all occurrences of each of its variables by anything we like. And we choose to replace r by p semicolon q and r dashed semicolon by p dashed semicolon q dashed, because that will turn the antecedents into merely restatements of the reflexivity rule for ordering. The conclusion, applying the same transformation, is written by replacing r by p semicolon q and r dashed by p dash semicolon q dashed, and that is the exchange law. So from the modularity rule, we have proved the exchange law. The other way around is a little bit more difficult. We assume the exchange law, and then we assume the antecedents of the modularity rule. I've copied the modularity rule into this box here, just to remind us. As a result, we can apply covariance to the consequence of the we can apply covariance to, in this setting, to replace the r here by p semicolon q and replace the r dashed by p dash semicolon q dashed. But notice now that this red left-hand side is equal to the right-hand side of the exchange law itself. So you can apply the exchange law and this line of the proof and use transitivity to derive the conclusion that we want, that this expression is below, which one? That one, which I've written here. But that is the conclusion of the modularity rule. That's the most difficult proof I will show you. Right. So, what are they for? Well, there are three distinct purposes for my collection of laws of programming. First and obvious purpose is to validate the program transformations needed for optimization. Any programmer who uses an optimizing compiler is thereby exploiting the laws of programming. A second purpose is to show how to execute a program step by step, thereby providing guidance for compiler writers and those who design interpreters for a programming language. Any user of a compiler based on these laws is thereby indirectly using the laws. And the third purpose is to provide proof rules to ensure that all executions of a program will exhibit some desirable property. Finally, we must assure ourselves of the consistency of the execution rules and the proof rules. And that I will do, I hope, quite briefly in what has followed. The first essential requirement to proving the rules is to define the primitive judgments of the proof rules and the execution rules. And the proof rules I will explain in terms of the Hoare triple, and the definition is given on this slide. Reading the definition intuitively, it says that if P describes what has happened so far, and Q is now started and executed to completion, then the trace of overall execution of P and Q, one after the other, will satisfy R, which serves the specification of what we wanted the program to do. For describing the implementation, the compilers and interpreters, we use the Milner transition. And the purpose of the Milner transition is not to prove the correctness of all executions of the program, but to actually obtain and present the results of just a single execution of the program. The Milner notation for the transition is shown and is defined as Q semicolon P is below R. And the interpretation this time is that R may be executed by first executing Q with P as a continuation for later execution. Of course, there may be other ways of executing R. Now we can check this definition corresponds with the intentions of Milner by a simple tautology, by translating Milner's prefix rule, which he used for CCS, one of the basic rules of CCS, and it's obtained simply by replacing this transition by its definition here. And we get yet another application of the reflexivity law. Now, the extraordinary thing is that these three rules are identical by definition. They can be translated into each other by translating one of them first into the modularity rule and then into the transition rule, and vice versa. It is by definition that the Hoare triple, at least for concurrency, the rule for concurrency, is just a translation of Milner's of the same law, which is the modularity rule. But I have already shown you, some length, that the modularity rule is equivalent to the exchange axiom. It follows, therefore, that both the separation logic and the operational semantics can be derived from the exchange axiom. And the exchange axiom can be derived from either of the two proof rules. So anybody who's ever used or believed in the validity of Milner semantics and Hoare semantics must agree that the exchange axiom is actually true. Shall we say, true of what it's intended to be true of the programs which these rules and laws are applied to. Now, a similar relationship can be established for sequential composition. In this case, we can prove it is equivalent to a weaker form of the law of associativity, in which the equality is replaced by an inequality in one direction. But it's not possible to prove the law in the other direction from the Hoare rule of sequential composition. But if we look at the Milner rule for sequential composition, we find that it's equivalent to the other weak form of associativity. Very similar, except that the sides of the inequation are reversed. Now, by the antisymmetry of ordering, the conjunction of the Hoare inequality with the Milner inequality gives the associative equation. At this point, we have shown that the algebraic laws provide a foundation for each of the two standard methods of reasoning about programs. And we have shown that the algebraic laws for concurrency can be derived from a combination of these two methods. This shows a strong mutual consistency between theories that the algebraic laws for concurrency are valid and should lead to widespread agreement among theorists. Sorry. Thank you. Unfortunately, this is not always so, as I will describe to you by recounting my own personal experience. Robin Milner and I were close personal friends, but we regarded each other as strong scientific rivals. I promoted the ideal of verification of programs, and my theories were designed to make this look simple. Robin's theory was more realistic. He wanted to describe things as they actually are, not as they should be. So he wanted his single theory to be equally applicable to computing and to the real world. And in this he succeeded. His theory is the one that is used now in biology. This caused him to concentrate on the actual behavior of a computer executing a program written in CCS, his program process calculus. In the 1990s, Robin and I collaborated on an extended project funded by the European Union. The third principal investigator was Jan Bergstra from Amsterdam, who promoted the algebraic definition of his calculus, which he called ACP, an algebra for communicating processes. The name of the EU project was Concur, and its goal was to reach agreement among the theorists on a unified theory of concurrency. After many years and many millions of euros spent, the project had not got the views of its leading theorists to agree or to concur, as suggested by the deliberately punning title of the project. And it's only after 20 years that I uncovered the essential unity of the algebraic, the operational, and the verification approach to concurrency, and indeed to programming. Whenever I'm tempted to feel proud of this revelation, I remember I should rather be ashamed that it took me so long to come to it. 25 years. Wow. Any credit for the discovery should, I think, be assigned to what has been called the unreasonable power of mathematics. It tells you more than you ever expected to know. So what's the point? The laws of programming provide the basis for the unification of theories of programming. A unification of theory is a necessary condition for technology transfer from science to engineering. It is also necessary for consistent integration of tools in a software development environment, for establishment of the subject on the academic curriculum of a school or university. So unifying theories, my original goal, as I said in the beginning, was scientific. Unification of theories is recognized as an important intermediate and ultimate goal for science. For example, the story of Newton's apple illustrates his realization that the same laws apply to falling apples and to the planets in heaven. Quantum theory is the closest that we have to a grand theory of everything. It had three independent discoverers, Heisenberg, Schrödinger, and Dirac, and they all put forward different presentations of the same theory. But they were prevented from fighting each other, or at least competing with each other, shall we say, by Dirac. Dirac discovered that the theories were mathematically identical. And that made it possible for him and Schrödinger and Heisenberg to win the Nobel Prize in 1932 and 1933. Because Nobel Prizes don't go to discoveries which are disputed among the experts. Unifying theories, the benefit of unification to the progress of science is that all the evidence which has been collected separately for each of the contributing theories automatically supports the unified theory which explains them all. And because all the separate theories are derived from a unified theory, each separate theory inherits the support given by all the other theories. This is important because the separate theories that have been unified do not get superseded. Their value is in no way diminished by the unification. They may be far more easy to apply to specific classes of problem and in specific circumstances than the unified theory. And that, I think, is the case for operational semantics and verification semantics. One of them is obviously useful for verification, and the other one is useful for execution. Both of them have a place in guiding the design of an integrated development environment for software. Now, technology transfer. If a practical engineer encounters two scientists who come into his office and promote rival theories, both of them are sent packing, with the instruction, please don't come back until you have resolved your differences. This happened to many researchers in Microsoft Research when they go and call on a developer in Redmond. So I'm told. The reason, of course, is that their managers and investors would insist that they must reduce the risk of the engineering project as much as possible. In other words, it's just too risky to design a project on the basis of a theory which does not obtain general agreement from scientists. The other thing is, if you base your product on an immature theory, and next year a more mature theory arrives, your competitors will catch up and overtake you very rapidly, and your product will become obsolete. Now, if you are engaged on a collaborative endeavor, for example, to engineer a tool set to be used by software engineers, you had better all agree on the specification of what it is that you are doing. Unification greatly reduces the risk of the expensive programming error, the most expensive error, a mismatch between the tools across the interfaces through which they communicate and collaborate. That is why modern toolsets exchange information in a common intermediate format, in intermediate code like Microsoft's Boogie, which has been given an agreed semantics, one hopes. This lecture has shown how the laws can be translated into rules of the kinds that are specifically useful to the implementers of different tools, and yet be completely confident that the intermediate code is being given the same algebraic interpretation on both sides of the interface. And if the algebraic interpretation is all that is required for the individual designers to design a correct compiler or verifier, then there is no risk of any gap in that interface. Finally, let's come to education. Education in computational thinking at secondary schools or in software engineering in professional education. If the laws are the definition of the language, teaching the laws will be, and have been used to actually implement the tools in the interfaces, they can be used in the interfaces between the programmer and the tool. And therefore, well, let's face it, the people who use any of the tools of software design engineering actually do know what the relevant basic laws are, which are common to the science and the engineering. Anybody against? Well, if you wanted to choose your antagonist, I don't suppose you'd choose Isaac Newton, but in fact he was against it, against the whole idea of using algebra. Here is a quotation from a letter that he wrote to Richard Gregory, which I have translated into more modern English. Our specious algebra is fit enough to find out, but entirely unfit to consign to writing and commit to posterity. It cannot and must not be published. Well, Leibniz was not so disparaging of his discovery of the differential and integral calculus, and maybe he deserves just a little bit more credit for realizing how valuable that particular mode of reasoning is. What Newton did was that he did use the reasoning heuristically, but his actual proofs published in the foundation, in the Principia Mathematica, were geometric. He used the methods of Euclid to demonstrate, because that really carried conviction. And I think he had something there. One of the real troubles, one of the real glories of algebraic laws is that they can be applied easily without thinking of what they mean. Whereas the diagrams that you draw to accompany a geometric proof, the little ellipses that he drew in the margin to illustrate the path of the planet, actually mean something rather obvious to anybody who looks at them. And people he preferred to use a method of reasoning that seemed more directly related to the space-time reality that his laws of motion were attempting to describe. How am I doing for time? 3 o'clock somewhere?
Just about coming to the conclusion.
Can I whip through a few slides? Good. So, let us try to draw pictures of what we mean by the variables that are used in the algebraic laws. I'm going to concentrate on the traces of execution of the program rather than the programs themselves, because of a theorem proved recently by a friend of mine, the laws of the traces carry straight through into the laws for the programs that can give whose execution is recorded in the traces. Now, what we're concerned with is events that occur in space and in time. So these can be drawn as dots, points, on a two-dimensional plane, just the one favoured by Euclid. These points are connected by vertical lines. Threads and objects are represented by these vertical lines, and the line passes from the top to the bottom, earlier to later, through all the points in which the thread or object engages. Now, an action is performed by a simultaneous, or possibly not simultaneous, event of both a thread and an object. And these are represented by connecting the event in the thread which triggered the action and the point in the object which carries out the action. Now, in a message sequence chart, which is what I'm working towards, the actions are given labels to indicate what type of action it is. And here is a list of possible actions that you might annotate the events in one of these charts with. So here's what I've done, a simple example in which an allocation action is the one that is the first action of the object allocated, and here the disposal is the last action of the object allocated, and in between we have writes and reads. Now, the arrows may also be labelled by values which are passed from the tail to the head of the arrow when that action takes place. For example, writing the value 4, reading the value 4, allocating a variable with value, well, this is written in hexadecimal, obviously, because it's the address of the object concerned. And finally, we get to what is often called a message sequence chart, which is already well known and widely used in the communications protocols and distributed system design. I suggest that it should be used in any tool which is attempting to help you to see what is going on while testing a concurrent program. Now, I need to define operators on these message sequence charts, which correspond to making a message chart of the sequential execution and the concurrent execution of the same program. So, what I will do is I will draw two message sequence charts, one for each operand, and then draw a red vertical line through the arrows which separate the columns of the chart. The arrows which cross the line are arrows simultaneously of the left-hand side and of the right-hand side, and they represent the interface, the dynamic interface of communications which pass between the two threads. And when we do a sequential composition, we just compose the two message sequence charts vertically, one above the other. Again, the arrows crossing the boundary represent the system state, the memory state, that is the final state for P and the initial state for Q. And these arrows belong to both P and Q, like that. And of course, since we can make these splits independently and again, a larger program, such as the one shown here, will have a message sequence chart of that particular form. I've forgotten something. The unit 1, here's a picture of the do-nothing message sequence chart. It contains no events, no lines, and no arrows. And since I have no time left, I will only say it's a good point to end my talk. Except I must thank you for being so patient with my exposition. We've listened to many of my strange ideas. You've been subjected to a mixture of detailed proofs and speculative philosophical musings. You've sampled a range of ideas which are normally found in different guises, in different academic courses, in different books, and in different articles. I will hope you will be rewarded by finding a use for some of the ideas in your own research and your own teaching, or in your own software engineering practice. But I hope you're also stimulated now to ask any questions on any of the, or indeed raise any of the points which I have wrongly omitted. And I'll thank you in advance for that too. Thank you very much.
Well, thank you, Tony, for such an elegant talk. And now we do have a little time for questions from the audience. You showed us various proofs which you constructed by hand, but I'm just wondering, what is the state of the art for automating proofs of the kind that you showed?
It's very good. This kind of algebraic proof really goes extremely fast, particularly using the prover 9, or indeed Isabel. And a proof like the one I showed you, which is actually a serious mathematical, semantical proof on which acres of journal print has been expended. Well, it's not worth timing. And whenever I have an intern, I ask him to verify all my proofs, which they usually manage to do without any difficulty at all. The advantage of algebraic reasoning is that it isn't too difficult for even school children, but it's really very easy for computers as well.
Other questions? Alan.
Thank you very much indeed, Tony. That was wonderful. I wish it were true that the things that you describe here I could directly teach to my students as an engineer, who tries to impart some engineering wisdom to computer science students. And I certainly talk about your work to them, but I'm troubled by your overall scheme because of the fact that those laws of science, although elegant and wonderful for teaching in classrooms, never proved to be very useful in my life as an engineer. And Newton's laws are good approximations when you're trying to draw an expectation of what might happen with a physical system, but actually they're not a precise, accurate description of how any physical system ever really behaves. It's never possible to know all the factors that influence the motion. So I would say that these laws of science are useful as approximations and as classroom theories, but not really for engineers. And I'm wondering if there's a variant of what you've told us that is a useful engineering approximation rather than a detailed proof mechanism.
I'm an idealist, and but I would dispute that you never use the laws. I've described several ways in which you use them indirectly. If they have inspired the writers of compilers, verification systems, testing environments, then that's quite good enough, because it's exactly what's happened in all the other branches of engineering. They do not use the laws directly. They don't differentiate and integrate anymore. They get computers to do it, and so do software engineers. So please, I will try to refute thus your initial assumption that you don't use the laws. Why shouldn't you admire them as well as using them? Thank you.
Another question.
Are you concerned that your presentation of the laws contains no account of what is meant by behavior, which is presented on the first slide as you could say one of the properties of a program? And are you confident that the definitions, that the constraints you've placed on what behavior is by your choice of these laws doesn't exclude programs that people might find interesting and useful?
No, I'm not confident about that, really. But I tried to make up this for this deficiency in the last few minutes of my talk when I introduced the message sequence chart as the appropriate form of a diagram which corresponds intuitively closely to what the computer actually does. And I will support this view by quoting the experience of those working on relaxed memory systems who draw just such diagrams. They call them, what do they call them? What do they call them? Event structures, perhaps. Litmus tests. And they draw these pictures with vertical lines and concrete line. And if they choose to define their memory model, which is, of course, an absolutely essential feature of concurrent programming by means of such diagrams, I'm very happy to take such diagrams and prove the laws from them.
Well, exactly, by virtue of the fact you can prove the laws, the constraints they place on what behavior is must be the same. And so has there been any attempt to explore what implementations, what manifestations of behavior are permitted with respect to these laws and which are excluded?
Well, there are quite a number of people in the audience who know the answer to that question much more reliably than I do. They actually working on testing hardware against the claims made of them by those who are making the hardware and finding litmus tests that will distinguish between what the designers say that they have done and what their hardware actually does. It's comforting to know that somebody's interested in that problem. It's very technical. The only reason I have succeeded in entertaining you for an hour or so is that I have ignored a very great deal of detail. All the details of reality are contained in the definition of the basic commands now. I think that the essential properties of the basic commands can very often be coded as algebraic laws. For example, which of them commute with each other, which of them are consistent with each other, and which of them contain programming errors, can all be described algebraically. And this sort of table of algebraic laws will convey a lot of information about the semantics of the program and of the programming language, graphically. Well.
Yes, Andy.
Coming back to what Alan was saying about applicability of these laws. I think we're all very encouraged by logic and algebraic systems that have been super successful in industry, like the sort of SLAM work or device drivers at Microsoft. And you mentioned separation logic, the exciting work that the folks at Facebook are doing, using separation logic to prove properties about systems. So, given your experience, it's really exciting that there's been such application to the industry of these tools over the last 10, 15 years. And you've been a keen observer. What sort of advice do you have for those people about what further directions to go in, where to redouble the efforts?
I hesitate to give advice to people who've been working in the field at the coalface for so long, when I'm only working in head office, as it were. I would suggest that the place that one might attempt to get a more scientific approach to, and a more widely acceptable one, is to concentrate on program testing. The most successful tools produced by Microsoft are all tools that assist with finding test cases that violate the assumption of correctness. If we can also give help, if we can make sure that any program that we fail to prove has a counterexample generated which serves as a test case, then that's the holy grail. But any progress in that direction would be, I think, not only scientifically interesting, an interesting engineering challenge, but also welcomed by many programmers throughout the world. Yeah.
Might I ask a question about algebraic versus, I suppose we could say, topological or limiting? I remember many years ago as a young PhD student reading reports from from PRG in Oxford, where I discovered, of course, the mathematical models we use in programming aren't all finite. For example, the factorial function isn't something we ever calculate, but it's used as a denotation of the values in that. And so we have a set of finite values that are described by algebra, but they then have a limiting case at the end. And I saw a lot of algebra here, and I just wondered if you'd looked at, for example, if you had a loop round these things, then some of the limiting behavior may just take you a little beyond algebra towards where you have topological structures occurring.
There's a wonderful article by Dexter Cozen on action algebras, in which he tackles this problem head on. He has found a complete algebraic definition of the Kleene star operator. In the case of recursion, one can apply Tarski's fixed point theorem to get the limits, to get a formal definition of the meaning of recursion as either the greatest or the least fixed point of a function. But the proof methods that you have to use are not strictly algebraic because they are essentially rules, the recursion induction rule. But apart from that, the algebra seems to bypass a lot of the questions that were originally of great interest to computer scientists, such as whether a function was computable or not. The algebra applies to uncomputable functions as well. The algebra applies to infinite executions as well. So there's nothing in algebra that says that the execution or the message sequence chart has to be finite. On the other hand, we can independently describe what it means to be a finite execution and use that as part of the specification of anything that we want to prove terminates.
Well, we've worked you very hard, Tony. It's been a wonderful lecture and question time. Probably a good time now to transition to informal questioning, lubricated by alcohol and canapes outside. And let's just end by thanking you once again for a wonderful lecture.
Thank you.